will also post the YouTube links on Kevin's website once he can finish uploading the video after the lecture. So last lecture we stopped right here, where we were talking about a general dissection of various modules inside the kernel, which is essentially they represent the various components you guys will be building over the course of this semester in that semester-long project I've been talking about. So you may wonder, given these two blocks, right? One is to this idea of build something from scratch whenever you need to address some data management needs. Basically, you do everything through some interface of your file system, right? That's obviously a viable solution, no matter what, right? Because you basically control how your data are going to be laid out on disk and how higher layer application gonna interface through your program with the data from the underlying file system, right? So this is one route. The other route is to use some sort of data management system, meaning that there is this level of abstraction. Then you interact with your data through that particular type of abstraction. Database management system being one of such abstraction. You may wonder what's the benefit for you to go with this route on the right rather than going through the route on the left. Well, there are a few benefits. Right? One is through this abstraction, for example, using a database management system, you get these things almost for free. You get concurrency control. We were talking about that example of millions of users accessing Amazon.com simultaneously. And if you're using a DBMS abstraction, you as an application developer no longer need to worry about how to do concurrent access control for this many users to access your data. Right? There is also this concern on crash recovery. For example, in the middle of a customer placing an order on Amazon.com, for some reason the background database system has crashed. For example, power failure or whatever, right? Or system bug. And what happened to the shopping cart of that customer? If your system recover from that crash, can you somehow manage to recover that shopping cart that user had already created right before the crash? And this is what we call crash recovery. And all of this are encapsulated inside a database management system, and that they provide a unified interface for you to achieve all of this without worrying too much about how to do that in your application level code. In particular, for example, crash recovery and concurrency control are provided by this abstraction called transaction from the underlying database management system. So from the application level code, you only need to write quote-unquote transaction rather than writing complicated p-thread code if you're using C or C++. Right? Does that make sense? And there are of course many other benefits that that will surface through the discussion of this course. Right? So to begin with, as I mentioned, we will do a quick review of some of the key concepts from a typical undergrad database class. But they are really important for you to understand before we really dive into the details of the kernel, right? So for that purpose, this lecture and maybe the 2 lectures from next week will be used for that purpose. Okay? We'll do a quick recap of key concepts such as relational model, relational algebra, and SQL. Then after that, we will dive straight into the kernel. Okay? So that's a roadmap for the next few lectures. So today we will start with the discussion of data model. So database, as I mentioned, if you look at the word of database, is a base, quote-unquote base, for data. Just like you have airbase, which is to store airplanes. And if you think about the airbase analogy, you have to know what type of airplane is going to be stored or coming to your airport, right? Whether it's is a fighter jet, or it's a Boeing 787, or it's an Airbus, whatever model, right? You need to know the type of airplane and the model of the plane in order to design the lot suitable for the airplane and the runway and so on and so forth, right? So in other words, you need to have some information about the model of the objects you are dealing with. Now, coming back to the database word, that's the Airbase example, right? But using that kind of analogy and coming back to the database word, what you need to know is this kind of similar information about your data. Because data now is your object. It's just like airplane is your object for Airbase, data is your object in a database. So you need to know the model of your data. And this is what we call data model. This is what we call data model. And there are, of course, many different ways you can model your data. And through the development of database over these many years, one particular model stands out to be, quote unquote, the winner, meaning the dominant representation of data in a database. And this is what we call relation model. And the most simplest form of relation model is to understand them as a table. Understand them as a table. And for example, there is a student table on the right hand side in this slide where you have a name of this table, which is student. And then you have a list of attribute and type information for each attribute of students in that student's table. And this is what we call the schema information of your data. Okay? Schema information about your data. What's so important, it looks like really, really simple model, but what's important to note is once you have these schemas defined in this particular format, you can actually imply the structure of your data. So what do I mean by that? What do I mean by structure of your data? So by looking at just this information, I know exactly each student record. What's the format of each student record coming into this table? I may not know the values of each such student. However, I do know the structures of each such student record coming into this table, even without looking at the specific records. For example, I know each student must have a student ID, which is a string type, and each student must have name, login, so on and so forth. Okay? And this is to be compared with and this basically implies what we call structured data. Much of the computer science, are developed based around what we call structured data. Meaning, if you think about any computer program you write so far, you basically start with some definition about the structure of the data you are going to process. Right? However, this is to be compared with what we call unstructured data. And increasingly, this becomes really, really popular for the reason I will explain in a minute. So what is unstructured data? Unstructured data means that you do not necessarily know the specific structure of your data. I'll give you one example of unstructured data, which is a key-value pair. That's essentially the dominant form of data representation in a key-value store, such as HBase or Cassandra, right? So key-value pair compared with, on this side, we have relational model. So this is a perfect example of unstructured data versus structured data. So what's a key-value pair? As the name suggests, it's just a key and a value. Just a key and a value. For example, I can also represent the set of students using a key-value approach, right? Where I ask each student record to have a single key, which is student ID, for example. And the value is whatever else that you care about. And what's the benefit of that? Well, if you take that approach, you don't have to predefine the structure of each student record. And in fact, you can be pretty flexible in what kind of information you want to keep for different students. I'll give you an example. For example, for some reason, for computer science student, I'm interested in the type of programming language they're most likely to use. But that field of information doesn't make much sense if you are storing students from, I don't know, a business major. Does that make sense? So if you are going to use relational model or structured data to represent students of that kind, what will end up happening? Well, you will end up having a lot of attributes that only a subset of your student record will have values for some of your attributes, and for some other subset of student record, they will have values for another subset of attributes. And the downside of that is you end up having a schema that's really, really long, overcomplicated than necessary in many cases, depending on what subset of data you're talking about. Does that make sense? So that's why key value approach become beneficial, right? Because in that case, I can simply specify student ID and value is just a collection of bytes. I don't really care what goes in the value field. I know it's just a collection of bytes. Then it's really, really flexible when you deal with, for example, student from CS, student from history major, student from business major, where you do want to store slightly different type of information for each subset of students. But there's no free lunch, right? If it's so good, why don't people just go ahead and use key value pair for everything? Well, there is obviously a trade-off, right? The trade-off is if you go with that, you don't know the internal structure in that value field. This makes it much harder at runtime for your program to process that information. As I mentioned last lecture, for example, in order to process a binary file, you have to what? You have to know the metadata information about that file. Similarly, if you go with key value pair, you have to know what's actually inside the value in order to do some meaningful processing of your data. Does that make sense? There is this trade-off, right? Structured versus unstructured. If you go with a structured representation, you don't know what these values, what the specific value is going to be, but you know exactly the structure of your data ahead of time. So you can write your program in a certain fashion even without looking at the values, because you know you expect every single record coming through your program to have this particular format. Meaning you can do a lot of pre-processing in your code to make your code much more effective and much more efficient. Whereas over there, you have to do processing somewhat on the fly, looking at the value, figure out, oh, what's the structure of this? For example, there may be a flag. You say, I go with key value pair. Fine, I'm going to reserve the first byte as a value, as a flag field, indicating what's the major of the student. 001 stands for CS, 002 stands for business, so on and so forth. Then I have some predefined metadata information, either embedded in my program or in some other metadata file I load before I start running my code, so that I look at the flag value, which is defined as the first byte of each value. Then I do an if-else branch to process the remaining values accordingly. Does that make sense? You have to have some sort of information about those value fields. But then the downside is there's no uniform view of your data because it's quote-unquote unstructured. So make your code much more quote-unquote expensive to write and expensive to run. Okay, but the trade-off is, of course, the benefit you get by doing that is you in terms of data management, data storage, you become much more flexible in terms of what kind of data you can actually store and process in your system. Okay, so that's a general kind of overview between the difference of unstructured and structured data. For the most part of this course, we're going to focus on this part, deal with structured data. But as I promised you, towards the end of the discussion, once we wrap up the discussion here, we will jump to the processing of unstructured data. Okay? All right. So data model. So why relation model? I think, first of all, it's used by a lot of database vendors. Second, really, the purpose, the main reason for relation model to become so popular is really because the needs of processing large amount of structured data. Okay. So to be more right? So that's what we call the schema. Then there's instance. What is instance? Well, instance refers to the specific records coming into that table. So looking at this example, the top, the first row is your schema of this table, the schema of this table. Of course, here for simplicity, I omitted the type information of each attribute. But imagine there should be a type information associated with each of these attributes. Okay? Then the instance is really whatever down below. Okay? In particular, this instance has 3 records. But one thing that's in common for all 3 records is they all conform to the same format and same structure. Okay? They can have different values, but they must all conform to this particular structure defined in your schema. Okay? And once you have this model, seems like a really, really simple model, you can then use powerful language interface to interact with your data. Fundamentally, that's because your data is structured. And because the data is structured, you can really design powerful language to enable simple and effective interaction with your data. Okay? And that language, in the context of database management system, is essentially the well-known SQL language, structured query language. And structured query language, you can broadly define them into 2 categories. One is what we call DDL, data definition language. The other is called DML, data manipulation language. And DDL is really for you to define the models of data and also define the instance of your data, meaning inserting, updating records within a particular schema. That's broadly going to DDL. And DML, data manipulation language, is really for you to do the retrieval of your data. Meaning, given a query, how do you express what you want in that query and get the results from the tables you have. Okay? Broadly speaking, there are two such categories. Here's a quick overview of SQL. We will later on we will have a more detailed diving view of SQL. Okay? But here's a quick overview of this language. You can do, for example, create table followed by the name of your schema and also the list of attribute name and attribute type to specify the schema of a particular table. That's create table. Insert into basically is to update a particular table with a new record, to insert a new record into a table, and so on and so forth. I'm not going to go over the list since we're going to dive into the detail of each of this. This is just a quick overview. Okay? So to give you some examples, for example, I want to create that student schema, as you saw a few slides back. And this is the way to do that. As you see, you use create table. That's the reserved keyword. Those are reserved keywords in structured query language. In this language, but student you can think about this as a parameter value you supply. You can supply any value of your choice to be the name of a schema, right? That you are creating, right? Then this part essentially is a list of attribute name and attribute type. And the type, there are many data types you can use in a given database system. I don't want to dive into detail today, but just give you a quick overview. Char 20, for example, stands for a character array of 20 characters. Okay, so in other words, it specifies a string. Alternatively, you can view that as a byte array because each character is just 1 byte. A character array of 20 characters essentially is a byte array of 20 bytes. I think, well, you can understand this data type as that. Then integer float, this goes without saying what it means. And to give you another example, you have table in row, you create table in row, that's another table you specify. Of course, here, note that using the create table statement, what you are really doing is to specify the schema of your table. It has nothing to do with the instance of your table, right? You're just specifying the schema of your table. What about I want to modify the instance of my table? Well, you can use insert, delete, and update to do that. I'll give you an example of the insert statement. You can do insert into student, followed by the list of attributes you want to specify a value for, followed by the keyword values, and then a list of values. The list of values and the list of attributes have a one-to-one correspondence relationship. Okay? And in some database systems, they allow you to ignore the list of attributes if you are inserting the list of values with one value for each of the attributes in your schema. Okay? In that case, you can actually ignore the list of attributes because the database engine will automatically, by default, if you don't supply a list of attributes, they will automatically, by default, view the list of values as one value for each attribute in my schema. Okay? However, there are cases where you may not be able to GPA value yet to specify for that student. Does that make sense? Yeah. Right? So in that case, I will specify values for all the other fields, the SID, name, login, and age, but I'm not able to specify a value for the GPA field. So in that case, you do have to supply a list of attributes so that the underlying database engine know exactly which set of values you are specifying for. Okay? Now, you can also do use delete to erase records from a given instance. The syntax of this query is fairly straightforward as well. You use the keyword delete from students, specify the name of the table you are trying to delete records from, and you have where specify the condition that must be satisfied for records to be deleted. A few words regarding this you can call this variable s. Variable s. What does it mean? Well, this variable s is what we call alias, right? Right? So essentially, in something, it's kind of like you are giving a nickname to the table you are working with, so that it can simplify the way you express your queries. Right? So, for example, here I use s to stand for student, so that in the condition expression part, I can say s.name equal to Smith, right? Rather than students.name equal to Smith. And another point I want to mention is in this particular example, since there's only one table involved in your query, you don't actually have to qualify the name attribute with a qualifier such as s of student. Meaning, even if I drop the s from the from and where statement, the intention of your query is still very clear, right? I can do delete from student where name equals Smith. Because from the context, there's no ambiguity which name field you are referring to. Does that make sense? However, that may not be the case all the time, especially if your query involves multiple tables. For example, there's the student table and the employee table. For some reason, you want to delete from students table where the student name equal to employee name. The weird organization says student cannot have the same name as employee. It's a weird condition, but for the argument's sake, we want to do that. And it so happened that both the schemas of students and employees have the attribute name. In that case, you do have to supply this qualifier, either students or S or employees or E, to clearly indicate, if you say name, which name field you're talking about. Is it name from student or name from employees? make sense? And in those cases, if you do not have alias, you have to write the full table name, which can be not so convenient compared to the use of alias, right? And so that's one motivation of using alias. Later on, I will show you another case where you absolutely have to use alias. That example is to be discussed later on. Okay, for now, you can think about alias as just a way of simplifying your program. Next, we're going to introduce a really, really important concept in the definition of relational models, which is the concept of keys. The concept of keys. So let's look at this particular example. I have student table, I have enroll table, and any person looking at this picture will quickly figure out, okay, you have students here, you have enroll here, and SID, this attribute, serve as kind of like a bridge connecting record from the enroll table back to the student table. For example, if I want to know the student name who got an A in topology 112, I'm not able to do that from just this table. What I will have to do is to look at the student ID value of this particular record, then go back to the student table and look up the name of that student. But the fact that you can do this is because that you have this particular field called student ID here. But imagine if I'm not using student ID here, rather I'm using, for example, age value here. Then you are replacing student ID column in this table with age of student here. What will end up happening? Can someone answer that question? Sorry?
Duplicate resolutions.
Excellent. You got duplicate records when you try to use age value to look up a student record from the student table. So this simple observation implies one really important fact, which is if you are trying to link records from one table to another, the value you use to link them must be unique. If your goal is to link to one particular record, this value better be unique. On the second, they are not physical, they don't physically exist in your database, right? They're just, I drew these blue lines for illustration purposes. So if you think about these blue lines, they really behave like this particular thing called pointers, right? If you know what pointer is. So I suspect most of you, if not all of you, know what pointer is, right? Or not? All of you know pointers? Okay, cool. So let's quickly recap what's the concept of pointer, right? How computer program works is that let's consider an object-oriented program. What happens is you have the definition of classes, and in the runtime for each class, you initiate one or multiple object instance conforming to that class. For example, there's a student class, you initiate multiple student 1, student 2 objects from that class. And each of these objects must conform to the structure of your class. For example, your class student have name, age, and so on and so forth. Each of these objects will have values for each of those attributes defined in your class. Does that make sense? And more importantly, each object will occupy a certain amount of memory space in the heap of your program, in the heap space of your program. And computer, your program operates over this object and the interaction among them. But in order to do that, the very first thing you need to do is know where each object locates at. Right? I mean, for example, if I want to pick up my key, I better know where my key is. Right? So this is what we call pointers. So you will have pointer pointing to the starting address of each object. Then through this pointer, you can manipulate this object. You can access information and methods attached to the object. So that's the concept of pointer. In some sense, this really mimics the behavior of pointers, right? So these are pointers back to the student record. These are your object. You have 3 student objects. In this case, then you have pointers linking to look into that. So as he has observed that this pointer is better to be unique. So to do that, with tuples, by the way, tuple in the context of this class, tuples and records, they refer to the same thing. Each tuple or each record simply refer to a row of values from your relational model, right? From a relational instance. Each record, each tuple simply refer to a row from your relational instance. So a set of fields is SuperKey if no two distinct tuples can have same values in all key fields. This is really important. Meaning that, okay, a SuperKey, first of all, is a set of fields. Okay? And no two records from that table can have same values on all key fields. So it's okay for them to have a subset of attributes to have same value, but not okay to have all same values on all fields. I'll give you an example, right? That's coming back here. Let's look at students table as an example. What is the example of SuperKey? Is age and GPA, this combination, age and GPA. First of all, it is a set of fields, set of attributes. Right? A set of two attributes. But is it a SuperKey? No. You said no. Why? Age has duplicate. But if you look at the definition of SuperKey, it says must not have the same value on all key fields, right? So your observation is only that age has duplicate, but that's okay because I have no duplicate if I'm looking at age and GPA as a whole, right? So is this still a SuperKey or not? Nika?
No, it's possible for people the same age to have the same GPA.
Okay, then Nika's response brings up another important observation, which is you cannot make the decision whether a set of fields is a SuperKey or not by looking at just a particular given instance. Yes, in this particular instance, if you look at this instance has only 3 objects. If you look at this one instance, yes, age and GPA seems to be a SuperKey because all 3 records, if you look at all 3 records, none of the 2 of them have the same values on both age and GPA. However, SuperKey is not to be defined against any one particular instance. It is to be defined with respect to the semantics of your application. If you look at, in the broader sense, in any typical given database where you have a student table, unless there is some explicit defined constraints, I will give you an example of such later on. Unless there is such explicit defined constraint, is naturally 2 students may have same age and same GPA. Right? So given this application semantic, you know age and GPA cannot be a SuperKey for that reason. But if you are given some explicit constraint by whoever asks you to build the database for them, things may change, right? For example, we may work for a university where it says, okay, in my university, all students with the same age, if that's the case, you must assign them a distinct GPA value. Sounds weird, but I may have that requirement. And when you do, that changes the game. Then age and GPA suddenly satisfied as a SuperKey. Does that make sense? Okay, so age and GPA is not a SuperKey. Can someone give me an example of a SuperKey in this case?
Student
SID. SID, this, first of all, it is a set of attributes because a set can have a single element. So it's fine. So when you see a key, you have to write it like this because it is a set. Even if it's just a single element, you have to really write it like a set. Right? So this is a set of attributes with a single element.
Name and login.
Name and login is another. Excellent. Name and login is another. Let's explain both cases. Why SID is a SuperKey? This actually is very easy, right? SID obviously is to be unique for different students, so no 2 records can have same SID value, meaning no two student record can have same values in all key fields. In this case, there is only one key field anyway. Why name and login is another super key? That's because you may have duplicate names, but you may never have the same login values. So any two student record will guarantee to have different values with respect to all key fields. Okay? So that's the definition of super key. But however, name and login, as he has suggested, implies another important concept, which is if you look at name and login. Okay, this is a super key. What about just using login by itself? Is this a super key as well? Yeah, it is a super key as well. So obviously there's a difference between the two. Right? They're all super keys, but somehow you observe that there's a difference, right? Right? There's a difference. Meaning, in some sense, login is more powerful in terms of distinguishing records for you compared to login and name. So to capture that, we introduce the concept of key. And the set of field is the key for a relation if two conditions. The first condition is actually the same as super key, meaning it must be a super key in order for it to be a key. The second part is where many of you may get confused on. It says no proper subset of the field is a super key. In order to understand this, you need to understand a few basic concepts, right? First of all, what is a proper subset? What is a proper subset? Well, given a set, a proper subset is any combination of a few elements, but not all elements from that set. For example, this is a set, right? The proper subset is login, name. What's the meaning of proper? Right? Proper subset means that it is a subset that's strictly smaller in size in terms of number of elements you have. If I just say subset, then the set itself is to be considered as a subset of itself. But when you say proper subset, that will eliminate the set itself to be a subset. Follow me? This? Okay? So, if you look at this definition, it says, okay, is this a key? Is name login a key? Well, we check the definition. Well, first of all, it itself, this set of fields themselves must be a super key. So condition 1 satisfied. This is indeed a super key, as we just discussed. And no proper subset is a super key. Now let's check. Name is not a super key because you may have duplicates. Empty set, obviously, empty cannot be used to distinguish anything, so obviously it's not a super key. However, login is a super key. So I found a proper subset that is a super key, which means this is not a key. This is not. But because I do have a proper subset that is also a super key. What about this? Is login a super a key? Well, if you look at the definition, first of all, it is a super key, and the only proper subset of login is empty set, which is not a super key. So this must be a key. However, you may have multiple keys for a given relation. So in this case, login is a key. SID obviously is another key. Right? Are these two the only keys for this schema? Well, if given no other additional constraints, seems like these are the only keys. But situation may change if I supply you with additional constraints. For example, let's go back to the age and GPA example. If I tell you, okay, in my university, if students are of same age, they must be given different GPA values. If I tell that this, based on the earlier discussion, age and GPA become a super key. Not only that, it becomes a key actually. Why? Because the only proper subset is name or GPA. And none of the two is a super key. So name and GPA suddenly become a key. So it really depends on what kind of constraint you have from your application. Okay? So that's the concept of keys. Once you understand the concept of keys, you will be able to understand the following. The first is primary key. You may have multiple keys. As we see from the student example, student ID and login both can be keys. What if you have multiple keys? Well, at the time you create the schema of your table, you choose one of your keys to be what we call the primary key. And the others not being selected will automatically become what we call candidate keys. Candidate keys. Okay? So here is how you specify that in SQL. You use the keyword primary key for primary key, and you use the keyword unique for candidate keys. So for example, by default, for the enroll table, the primary key obviously is a combination of student ID and the course ID. And primary key actually implies a lot about the semantics of your application. For example, if I use SID and course ID as the primary key, what that actually implies? What's an important semantic being implied by the fact that SID and course ID is the primary key for the enroll table?
The student can take the same course.
Student meaning you cannot fail a course. If you fail, you are not able to take that course again. So if you go into a university, either you ask the registrar office, can I retake a course if I fail, or simply ask, what's the primary key of your enroll table? But good luck if you ask the second question. But maybe you are lucky, the registrar office has an intern student who just finished taking David's class. Okay? So, but you see the point, right? Now, but what if I also tell you, in addition to the default, which is student take on the course once, but I also give you the additional constraint saying that, let me finish this and take your question. The student can take only one course and receive a single grade for that course. Furthermore, no two students in a course receive the same grade. No two students in a course receive the same grade. I see some professors do that actually, meaning that I want a strict ranking of all students in my class. There is no tie. And let's say this is not a letter grade, because that would be too brutal, right? If I say no tie on letter grade, you guys probably will quit my class, right? So when score as your grade, right? You get 98. Is I want to enforce the constraint that no two students which is course ID and grade. Right? Because the combination of these two is unique. But they are only unique given that constraint. If I never specify that, naturally in most applications you would not assume this, right? Two students of course can have same grade in a course. Unless you are told there is this additional constraint posed by the instructor of that course. So by default, this is not a candidate key, but if given that constraint, they suddenly become another key. And if you choose this as your primary key, this automatically becomes your candidate key. And you use unique to specify candidate keys. Now, back to your question.
So in primary key, it is SID and CID. So SID, is it the collection of both, or because SID will be unique and a SuperKey?
Okay, fantastic question. So in the enroll table, it must be the combination of the both to be a key. Because if you look at the enroll table, SID itself is not unique because the same student actually can take different courses. You cannot take the same course multiple times, but I can take multiple courses. So SID, neither SID nor course ID by itself can distinguish record from the enroll table. In other words, you do have to use a combination of the two to form a key. Okay? Now, once we understand the concept of SuperKey, the key, and candidate key, now we are ready to introduce foreign keys. Foreign key is actually, in my opinion, the easiest one to understand. Foreign key simply says those attributes in one table, they are a key from another table. If that's the case, this attribute in the current table becomes a foreign key. So for example, SID is a foreign key to the student table because SID is the key of the other table, either a primary key or candidate key. And you can imagine course ID is also a foreign key referencing, imagine the course table, to tell you the detailed information regarding the course, like the session number, the venue, the course you meet at, the instructor, and so on and so forth. Okay, so that's the concept of foreign keys, and you specify foreign key using this syntax, a foreign key followed by the attribute or attribute where this attribute or this set of attributes is actually a key in another table. Okay. Go ahead.
Is there any practical difference between the and the candidate key?
Very good question. Is there any practical differences between a prime key and a candidate key? The answer is no, really. I mean, it's really a design choice made by the database developer as which key you want to use as your primary key. And typically, people use the one that you reference the most if you have multiple such keys as your primary key. For example, key mass ID and login. Naturally, you will argue that in most applications you will use SID more frequently than using IDs, using login. So even though both are keys, for that reason I probably will go with SID. Okay. Now foreign key, so we're done with foreign key. And integrity constraint. So foreign key introduced an important concept called integrity constraints, or in short, ICs, integrity constraints. Integrity constraints specify that a set of constraints that must be satisfied by any instance of your table. And this brings up this concept, what we call legal instance, a legal instance. A legal instance is an instance of your table that satisfies all constraints set forth by your schema. I'll give you an example of a legal instance, right? If we go back to the student table, imagine age field. The type of age actually is integer, right? So this is a legal instance. But if I insert another student record with age 19.5, for example, I want to model the fact that student is somewhere in between 19 and 20 years old, 19.5. Good intention, but unfortunately it becomes an illegal instance with respect to your schema, because your schema said age must be integer. And if you do want to model the fact that somebody is in between 19 and 20, then change the definition of schema, make age a floating or double type, so that it can accept such information. So that's the simplest example of integrity constraint, ICs. There are more sophisticated examples. I'll give you another example. Let's say in my university, one admission rule, I mean, again, this is only a hypothesis, right? It's not a real world example, right? Let's say I have some minimum age requirements for admission. Let's say I only admit students who are at least 18 years or older. How do you specify that constraint? You can no longer say age is an integer to satisfy that constraint, right? Because I can perfectly okay insert a new record saying student ID name, login at age 16. That's totally fine because it is an integer, right? You need some additional machinery in order to enforce such constraints, right? And we will give you example of how to. We will talk about how to do this later on. Okay. For now, we just try to understand the concept of IC and some really simple example of ICs. One is those type information from your schema. Another form of integrity constraint is actually specified by the usage of foreign key. So before I dive into the detail of that, let's come back to the pointer example. Okay, one thing that if you ever write any C or C++ program and you use a lot of pointers, and you know what the typical procedure or a more formal word for that is you want to deallocate the memory space of this object, then you delete the pointer to free the memory space. If you don't do that, what happens? This is what we call memory leak. If you don't do that over the time, the longer you run your program for, there are more such ghost objects floating around, eating up your memory space. Like Chrome, take Chrome browser as an example. In the early stage of Chrome, in fact, I think Chrome still has a little bit of that problem. If you let Chrome run, even without you are doing anything, over time it eats up all your memory space. The way you can fix that is close the browser and bring it up. When you close the browser, what happens? The underlying operating system will deallocate the heap space of that program. Then all the objects associated with that program will be deallocated automatically. But this is a brutal way of what if I'm watching a World Cup live game that runs for 24 hours on Chrome, on YouTube? I don't want to close my browser, but it's eating up my memory space. What do I do? You're stuck, right? In that situation, unfortunately, you are stuck. And you may wonder, if I close browser right now, what's the big deal? Well, maybe there's a goal in that 1 second. You know, this life is like that. When I was, when I used to be a big soccer fan, and when I watch a soccer game in a club, I want to go use restroom, but I hold on to it because I'm expecting a goal, and it's new all the time. Finally, I cannot hold it anymore. I run for the restroom, come back. You know what? There's a goal. 1 in a million chance, but it happens. It's just like that. Okay. So you cannot do. So the proper way is to deallocate for Google developers when they are developing the Chrome code. Deallocate the object right properly. But if somebody, the two things may happen in this process. One is you may do this in wrong order. Like use S2 example. I delete the pointer first. Then I try to deallocate the object. You know what? What happens now? You can no longer find the object to deallocate if you delete the pointer first. Right? So this is not okay. So the developer says, okay, fine. I'm not going to delete my pointer first. I'm going to deallocate my object first. Then I delete my pointer. You know what? What may happen in this case? Well, you may forget to delete your pointer. So you delete your object, right? Because deleting pointer first is bad, as I just explained. So you delete object first. But then you forgot to delete the pointer. What happens now?
Crash.
This introduces another famous problem, or infamous, whatever you want to call it, dangling pointer. Dangling pointer leads to what we call secondation fault. Secondation fault means you are dereferencing an object when it no longer exists. You are using this pointer to refer to a student object that no longer exists. And this leads to secondation fault. Because you are expanding, okay, I'm using this student pointer, I'm expanding the first 2 bytes, here represent a student ID, but since you deallocate the object, operating system use the space for something else, this becomes some junk, or whatever. And if you use pointer to dereference your object, at this point, something will go wrong, terrible wrong, your program will crash. And in fact, this not only is a bug in your code, this also may bring security concerns. Right? One famous attack, security attack, is buffer overflow. You overflow your buffer so that you actually get into the heap space of another program. Once you're there, you can do whatever you want. You're not supposed to access the heap space of another program, but if you do buffer overflow, you can. And it's all related to this, right? So all this discussion come back to the concept of foreign keys is basically they translate to integrity constraints. Okay? They translate to integrity. If you understand this, you should be able to understand what I'm about to say in the next slide. So in other words, looking at this example, but coming back to the database context, what do I mean? Okay. In particular, essentially, you are trying to answer this question, right? What should be done if an enrolled tuple with a non-existent student ID is to be inserted? Well, the answer for this seems clear, right? It's just reject it. If you try to insert new enrolled record with a student ID that doesn't even exist in the student table, how can this possible be? You are telling me there's a ghost student trying to take my class? No, it's not going to happen, right? So this decision is simple. But what if a student tuple is deleted? That's kind of like you are deleting the object the pointer points to. Right? That's the same example I just went over there. A couple of things, and if you do nothing about it, obviously this is the bad situation, right? If you do nothing about it, if I delete the student record and this is a pointer, this is a foreign key, you do nothing about it, you have a dangling pointer, you may have secondation fault. So you have to do something about it. You can also delete all enrolled tuples that refer to it, meaning delete all pointers pointing to this object. By the way, it's similar here. You actually may have multiple pointers pointing to the same object. And that's the primary reason you may have secondation fault. If you have only one pointer pointing to a single object, typically, if you are a trained developer or programmer, you will do a good job in deallocating delete that pointer too. But oftentimes, people write code, especially in complex systems, for the convenience of your coding, you may say, okay, what the heck, I'm not going to keep track of all the pointers. Whenever I need, I just conveniently introduce another pointer. Yes, it makes your programming much easier, but if you do that, at the end of the day, you know what, I guarantee, if you keep doing that, you will forget to deallocate some of the pointers. And you may end up with separated. So, delete all in-row tuples referred to, not just some of it, all of them. Yeah, delete all pointers. Right? That's choice number one. Choice number two is disallow deletion of a student tuple that's referring to. This may be useful in the situation where you say, okay, if you are in the registrar office, you say, okay, a student can only be deleted from my university database if he or she has finished taking all classes and we no longer have any record of this student in the enroll table. If that's the case, you want to enforce the constraint in the second fashion. Meaning, if somebody accidentally trying to delete a student who has not finished all the classes, you should disallow the deletion of that student. That's essentially choice number two. Choice number three is, if somebody delete this, one choice is instead of delete all these pointers, there's this concept of a pool of pointers, right? You can put all these pointers back to the pool and reuse them later on. Basically, ask them to point to some special place or have some special flag attached to these pointers. Rather than deleting these pointers altogether, you recycle them somehow or keep them around. Okay, so that's kind of the idea of the third approach, which is, and this third approach is really useful in the context of data analytics, right? For example, I'll give you an example. If a student graduates from my university, okay, fine, go ahead and delete that student record. But I do want to keep the enroll information of all students around, not for the purpose of analyzing that one student, but for the purpose of analyzing, doing some overall analytics of my student population from the past. For example, I want to know the average grade of all students taking topology 112 class. For that purpose, I need to keep all enroll record around, even if the students corresponding to that enroll record had already been deleted or graduated from my university. But I no longer care about the student ID field because I'm doing aggregation analysis now, average or some kind of aggregation analysis. So I no longer care about the specific value of the enroll ID. In those cases, I can set enroll ID, it's the student ID in the enroll record if a student is to be deleted to some default value, right? Whatever that default might be. So those are different choices. Now, lastly, I want to briefly talk about relational query language. The DML, data manipulation language. So here is some really simple example of DML. For example, I want to find student record with age value rating. You do that using select heuristic from students where student age equal to 18. So one powerful thing about structured query language is really intuitive, right? Most of you may have some SQL experience before, but some of you may not have any SQL experience before. Even if you don't have any knowledge about SQL, looking at this statement, you can figure out, without even me telling you, you can figure out quickly yourself what it does. You may not know how to write this language yet, but you can understand this language perfectly. English is such a language, I can come to US and without learning anything, I can at least understand what you're saying. I don't know how to write, so you can say good morning, I understand what you're saying. So I don't know how to say back to you, but whatever you say, I understand. That's cool, right? That's pretty cool, but unfortunately, no, right? You have to really work hard to pick up a new language. So SQL is really powerful, really intuitive in that sense. And part of the reason SQL can be like that is really because we are dealing with structured data. It goes back to structured data. Right? Because you're dealing with structured data, your language is well structured too. And that's why you can understand this language without any problem. Okay, so let's give another example. The heuristic here means all records. I'm selecting, sorry, not all records, all attributes. I'm selecting all attributes for all records satisfying the conditions specified in the record. Let's continue this example. Let's say I'm not interested in all attributes. I'm only interested in name and login. So I will select student names, login from student where age equals 18. Okay? Now, this example here illustrates yet another important concept in SQL that we actually a heavy part of this course study for, which is this language specifies what you want, but not how you do it. For example, you only tell the database system, I'm looking for student age 18 with these two attributes. You're not really, if you think deeper about it, you're not really telling the underlying system how to go about doing this. You may wonder, what do I mean by that? Well, let's think about how you're actually going to do this. The naive solution is very simple, is you scan through each student record, right?
Yeah.
For each record, you check whether age value is equal to 18. If it is, you return the age and the name and login value of that record. The cost of this approach is linear to the number of records you have. Is there any alternative approach you can do? Well, depends on how you organize your data. Suppose your student table the records are sorted with regard to the age value. They can do a value search. Instead of linear time, you pay logarithm time. Does that make sense? But the key point is, in this language, different from C++, Java, Python, all the language you guys used before, you never really specify how this is done. Imagine if you do this in the operating system route, the blue route we mentioned earlier, what you have to do? Well, you have to open the student file, write in your code, whether it's a for loop for I equal to 1 until n is the number of records in your file, that's a linear search. Or you say for I equal to the middle value, then I do this. If it's less than, I recurse on the left-hand side, otherwise I recurse on the right-hand side. In any way, in any case, you program have to specify how to do it, not only what to do. There's what and how components in every program you guys have written so far. Make sense? You may argue, wait a minute, no, the way I do it is I call some API. For example, sorting, take sorting now. I want to sort my data. I don't tell the program to do bubble sort, which is the first one compare with all the remaining ones. If it's smaller, swap. Go with the second one, continue this. Or I do quick sort, which is selecting a keyword and partition them into smaller and bigger set, recurse. I never really do that. I always say sort. I call a method called sort. Other than that, I'm telling the underlying system what to do, but not caring about how to do it. Well, that's because somebody else has packaged that method into sort. And if you really care about efficiency of your program, you actually want to look at how that sort method is implemented. You may call sort A or sort B, two different methods. One is bubble sort, one is quick sort. You actually, in that process, specifying how to do it, not only just what to do. But in SQL, you don't. And this goes back to, if you recall the overview discussion I had, that we have the query plan generator and query optimizer. What really happens in a database engine is whenever you specify something like this, the underlying database engine will generate different possible plans to do the same thing and choose the most efficient one out of it. And how to do this automatically is really the one cornerstone of a database kernel, which is what we will study for the most part of this course. Okay? But for now, we are still at the application layer, right? You don't have to worry about this. You view this as a black box. I just tell you what to do. I don't specify how you do it. And this makes you like a boss, right? That's essentially what a boss does. A boss does what? Never does how, right? I just tell my employees who work for you, like what I want. How to execute, that's what I pay you for. No? That's what everybody wants to be a boss, right? Okay? So that's the what and how argument. And this can go in that slide. In this case, I'm looking for data that really require the interplay of multiple tables rather than a single table. So here I'm saying, okay, I want to find the name and course ID for all students between students and enrolled, right? This requires everyone operation. And the join condition is specified in our where clause where you have s.sid equal to e.sid. And this is where I mentioned earlier the alias concept becomes really convenient because you can now use s and e to specify SID from student and SID from enrolled respectively, rather than using students and enrolled all the time, which is a little bit less convenient to write. Okay, so you got the results. So what's really going on here? Well, semantically, what's going on is, from the from clause, you are computing a cross product of all input relations. What is a cross product? Cross product is a full matching of all possible pairs of records from two given relations. A full matching of all possible pairs of records from two given relations. So for example, the first table has 2 records, the second table has 3 records. Then the cross product of the two has 6 records, which is the pair of first record from the first table with each of the record from the second table, and that gives you 3 records in the cross product already. And all the pairs of second record from the first table match with all the records from the second table. You have 3 of them, so that gives you another 3 records in the cross product. Altogether you have 6. Okay, so that's the definition of cross product. Really, really simple concept. So the first step, you compute the cross product from the from clause. Then you check the where clause against each record in the cross product. And then finally you do the select clause. So this example of illustrating what's happening in the query before. So this is each student record paired against each enrolled record. So that's the cross product we got. And going through the cross product, now you're looking for the record that's satisfying your query condition, which is course student ID equal to student ID and grade equal to 8. So there are only this record highlighted in yellow color satisfies both conditions. Student ID equal to student ID and grade equal to 8. Then you put that out the course ID and the name of the student. And if you think about this approach, it's very intuitive, very easy to understand, but unfortunately this is very inefficient. Why? Why this is inefficient?
It is like cross product, taking out cross product will be already n cross n, which will be...
Yeah, n squared, right? If you assume each record of n size, meaning n record in each table roughly, then this approach for 2 tables, for joining over 2 tables, the cost of this is n squared. Because no matter what you do, you have to write out the intermediate results, which is the cross product, has a size of n squared already. You have to write each of them out, this takes n squared time already. And if it's 3 table join, this becomes n cubed. Quickly this becomes so expensive you cannot afford to do this. I mean, imagine if you're in Google, each table has billions of records. N squared is like an unimaginary big number that you cannot afford to do, obviously. Okay? So this approach never scale in practice. So in practice, this is not the way database handle the join queries. But this goes back to the very point I was trying to make earlier, which is the beauty of database system is allow you to specify what you want to do, not how to do it. So underlying the engine, this is never the way they handle join queries. And we will talk about later on how join queries are actually being handled. But that being said, this is still a very intuitive way for you to understand what that query does. But this is not really how the query is to be executed. Okay? Okay, I think I'm done with the summary of relation model. Let's quickly close this and move on to the second part of the review, which is relational algebra. So now we understand relation model. Now before we dive into SQL, let's formalize the theory and foundation behind the design of SQL. In fact, this particular language relation model is going to be used to represent the query plans generated from an input SQL statement. So as I said, if you recall what happened, the big picture, right? Some user read a SQL statement, it will be compiled into a query plan. And you need some internal representation of that query plan. It's just like in any given program, if you write a C or C++ program, yes, you write your code in C or C++, but the underlying machine doesn't really understand C or C++. It understands whatever instruction set that machine's architecture is able to support, for example, x86. And those are a different language. For example, known as assembly language. So somebody needs to convert your code in C or C++ into that assembly language representation in order for the underlying machine Java you're using relational algebra being quote-unquote the assembly language of the database engine. Okay? Make sense? Okay. With that being said, let's dive into relational algebra. There's some overview I will skip, and I will dive into the detail directly. So, a relational query expects relations as their input, either one single relation or multiple relations. For example, if you think about a join query, that's obviously an operation over multiple relations, not a single relation, multiple relations. But if you think about the other example we mentioned, for example, find name and age of find the name and login of students who are 18 years old, that involves just a single relation. Right? So broadly speaking, I have what we call unary operators, meaning involve only a single relation as its input, or binary operator, involve multiple relations as its input. Okay? I will come back to this slide later on, which basically says once you understand the input to a relational query are relations, you will quickly realize that the schema of the input is fixed because you are supplying a relation and the relation has a fixed schema. So this is fairly easy to understand. But it's a little bit tricky to understand that not only the input schema is fixed, the output schema, as soon as you supply the operator as well as the input relation, the output schema is fixed as well. The output instance might differ depending on what kind of instance you supply, but the schema information is fixed. And this can be a little bit tricky to understand at the moment, but once we understand a few operators, we will come back and reinforce the understanding of this problem. Okay? So, relational algebra is really simple. It has 5 basic operators, and those are the 5 operators you need to understand. Once you know this, you can express a lot of powerful queries. The first operator is selection, represented by a Greek letter sigma, projection, represented by a Greek letter pi, cross product, segment, and union. We start with obviously, selection and projection are unary operators. The other 3 are binary operators. And we will go over each one of them one by one. And the other fact to note is that a relational algebra operator takes relational instance, relational schema as input, and most importantly, produce relational schema and relational instance as output. What this implies is actually you can combine or compose multiple relational operators together to form a more complex operation. Why? Because the output from a relational operator is a relational instance with a relational schema. This obviously can immediately be used as input to the next operator in the pipeline. Right? So you can compose them in this sense. Right? So let's look at this example. Let me introduce the example. I'm going to use this sailors club example. I have boats, reserve, and sailors. And for sailors, I have the same schema, but I have two slightly different instances for the same schema. Okay, basically this database is showing you which sailor reserve which boat at a sailor club. One important note is if you look at the reserve table, the primary key is underlined, and the primary key for the reserve is the combination of SID, boat ID, and date. What that means is the same sailor can reserve the same boat multiple times on different dates. However, the same sailor can only reserve the same boat once on a given date. Okay? So let's start with projection. What projection does? The notation of projection is you use the operator pi, supply a list of attributes as its subscript, and then supply a relational schema as an input to your projection operator. And what it does is to quote unquote select the columns listed under what we call the projection list. For example, project out age from S2 and project out name and rating from S2. Very simple to understand, right? So let me give you some specific examples of this. So if I put that name and rating, that's what you get. You are selecting everything from that column. So rating and age is simple. Rating and serial name is simple. What if I put that on age? What's the result I get? Well, you may argue I should get 35, 55, 35, 35. Right? However, the result is actually 35 and 55. This goes back to what I said earlier. Remember, a relational operator produces a relational instance as its output. And what's the fundamental requirement for a relational instance? No duplicate. Age values in the original input instance, that is because you have additional attributes so that the record as a whole has no duplicate. But now once you do the projection, what is the output schema? The output schema becomes age, this single attribute. So the output schema is just age. Alright? And which means age now is a key. Right? This is the only attribute you have. Meaning you cannot have duplicate. So you have to eliminate duplicate from the output of the projection operator. Why we are not doing that here? Well, essentially we are doing that as well here, but it so happens that there are no duplicate to be eliminated from. So there's nothing you actually are saying on the output side. But this duplicate elimination is needed for the projection operator. Now, looking at this example, I will emphasize again what I said earlier, which is given a relational operator, the input schema is fixed. And in addition to that, the output schema is fixed as well. For example, in both cases, the input schema is just a schema of the Saylor's table. The output schema, without looking at this, I know must be name and rating, and I know for that must be age. The output schema is fixed as soon as you supply the operator and the schema to the input of the operator. So that's the projection operator. Now let's look at selection operator. Naturally, if you can quote-unquote select columns, you should be able to select rows. So that's what selection does. Selection select a subset of rows from the input schema by looking at a condition that's supplied. For example, this is the condition, this is the input, and the output will be a subset of your input. So the output will be just these two records. Speaking of that, because you are selecting a subset from a set, you actually you don't have to worry about duplicate elimination for selection. Why? Because the input is a relational instance, which means it's duplicate free. If you are selecting a subset from a set that's duplicate free, the subset guaranteed to be duplicate free. If you have a bag of balls of different color, you select a subset of balls, they guarantee to be color different, right? If you can manage to find two red colored balls from a bag of balls with different colors, you go American Got Talent. No? I am a big fan of watching that on YouTube. Some people do that. They show you a color of bag of balls, and maybe not balls, and they make it more dramatic, right? Color of, I don't know, whatever dramatic object I think of. Then you select and you get same color out of it. Well, surprise. But now having it, okay? Selection, you don't have to worry about elimination. Now, another point I want to illustrate here is the output of a relational operator is still a relational instance. So it can be used immediately as input to another operator. So you can compose operators together. So I can compose this together with the projection to get what I want in the end. Does that make sense? Instead of rushing through, I will stop right here. So a quick comment about next week. So unfortunately, I will be out of town next week to attend WellDB conference in Munich, which is a top database conference. We have a paper to present over there. But I'm not going to cancel the lecture because it's a review of undergrad concept, right? So I will ask my PhD student, W.D. Paul, to substitute 2 lectures for me. He will continue the discussion on relational algebra, then continue the discussion on SQL. I hopefully by the end of next week, he will finish the discussion of both. so that when I come back, we will be ready to dive into the kernel. Okay? All right. Yeah, I will.